My name's Grant Cardon. I'm the Extension Soil Specialist. And in Extension, we don't normally stand in one place when we're talking. This is going to be hard. Since I'm on camera, I want to be able to, have the people that are streaming feel like we're interacting with them too. So if I disappear for a while for you guys online, I apologize. It's just it's the moving nature in me that's going to dictate that a little bit here and there. We're going to talk today about nutrient cycling, sampling, and things like that in fruit crops. We're going to take it from a very general level, but a detailed general level, so that when we talk about the things that we do, you're going to have a basis for the why of it at the end, I hope. Those of you that had a chance to go through the initial questions of knowledge and things like that had to do with this, that gives you that kind of example, that there's the why things that we're going to go in to be able to answer some of those questions that we had at the beginning of all of this. So let's just start off with, what are the nutrient elements? What are the things that plants really need to grow and to thrive? You see a list of them here. There's some 16, 15, 16, depending on who you're talking to, maybe even 17 in some cases, depending on individual perspectives on different elements that are needed by plants, that we consider to be the nutrient elements. Of course, carbon and hydrogen are like the main building blocks of any living thing, and so those are right up there, carbon, hydrogen, and oxygen. But those things, plants and animals typically obtain from air and water directly. All of the other nutrients come from soil materials from one source or another. And so most of the nutrition of any plant or animal is going to come from the soil. And so we have a lot of elements here that we're going to talk a little bit about. The three then that we would consider those that we would manage, the big three, are nitrogen, phosphorus, and potassium. And you're well aware or acquainted with fertilizer materials, and those are the things that they, when you get a guaranteed analysis fertilizer material, it'll have the content of those three particular nutrients stated right in prominent lettering, numbering on the material itself. Well, why are we interested in nitrogen, phosphorus, and potassium? Nitrogen is the primary constituent of all the proteins and the enzymes and the DNA and other things in the plants. All of the functional organs in plants rely heavily upon nitrogen as a base for those structures. And so chlorophyll, for instance, is full of nitrogen. All the enzymes that process and build and destroy and recreate the proteins, all of the proteins that have to do with mitochondrial function and processing sugars and processing nutrients in the plant cell, all of these compounds and structures are really heavily rich in nitrogen. DNA, for instance, that tells the cell what to do and what it is in the first place, is full of amino acids which are high in nitrogen content. So nitrogen is like the biggest one we worry about because it's so dynamic, it's used in so many different structures, and so important to the function of the plant that we focus a lot on its management. Phosphorus is another really important one. It's a constituent of some of the proteins, but it's also really primarily responsible for energy storage and transfer in the plant. How many of you remember from basic biology the structures ADP and ATP? Those were the major energy storage and transfer compounds within the plant. Those are phosphates that are found inside the plant. So phosphorus is a huge part of those particular structures and compounds. It's also really important in root development and root function and structure. And so we worry a lot about phosphorus fertility in a new orchard setting or a new planting or things like that, where we're interested in promoting the development of the root system. Potassium is the next big one. Potassium is responsible for a lot of the transfer of nutrients within the plant through different cells and structures. Interestingly enough, compared to phosphorus and nitrogen, potassium is not found in any physical structure, not in a tissue or a physical structure. It stays as a dissolved ion in solution, but its function is to facilitate the transfer of all of the other ions and the nutrients and things throughout the cell. And it's primarily responsible for the function of the pores in the leaf, opening and closing the pores in the leaf, allowing for exchange of gases and water vapor in and out of the leaf. And so potassium is critically important in water relations in the plant and controlling the flow of water, and hence also then the flow of nutrients into the plant. And so if we're deficient in potassium, we don't have good water relations, we don't have good leaf function, we don't have good fruit development and other things over time if our potassium nutrition is off. So those are the big three that we look at, and those are found at percent levels in the tissue in terms of the content. So parts per 100 is percent, and they can be even in parts per 10 at higher percentages in different structures within the plant. All of the other nutrients are used at much, much, much lower degrees in the tissue. In fact, most of the others that are listed there, calcium, magnesium, boron, chloride, and so forth, are found in parts per million, parts per billion levels in the plant. So very, very little of them in comparison to nitrogen and phosphorus, but not any less important to the overall function, and we'll talk a little bit about that as we go along. So I provided this table for you just so you can see what the nutrient elements are and some of the important functions that they perform within the plant. What we really want to know is when I'm managing those primary nutrients and even the secondary or micronutrients in the plant, what are the things that each of those elements is going through in the soil, in the plant, so forth, the cycling that's taking place. So I have some idea of why I manage these nutrients in certain ways and why we deal with difficulties in managing some of these nutrients in our western Utah soils. Or Utah soils in general, western United States in particular. So let's take a look at the cycling of these different nutrients. We already talked about the primaries being nitrogen, phosphorus, potassium. So, yes?
Why is carbon not shown as the source of soil? Isn't biochar supposed to be a good nutrient?
Okay, good question. Why is carbon not listed as a soil nutrient, a soil obtained nutrient? Carbon is not obtained by the plant through the soil. When we add organic matter, which is high in carbon, to the soil, it's a food source for the microbial population within the soil. And the microbes are responsible for a lot of the cycling of those organic matters, breaking them down so that it releases the other mineral nutrients back to the system. And so organic matter, carbon sources, organic carbon sources, are really food for the fungi and the bacteria and the living things besides plants, the animal side of things in the soil. They keep the soil healthy. They keep it processing all of this other material and releasing the nutrients found in some of those organic materials, and the changing and altering of the nutrients into forms that can be used by the plant. But the plant does not take carbon up directly from the soil. The plant obtains its carbon from carbon dioxide out of the atmosphere as it's absorbed through the leaves and then converted within the plant. Okay, I hope that answers that question. Good question. Sulfur is oftentimes included in the primary nutrients. It can be used at higher contents than parts per million, parts per billion. And sulfur is also important in chlorophyll and some of the other structures that help process sunlight and conversion of energy into sugars in the plant. And so we'll talk a little bit about it and deficiency as we go along too. But generally, in our soils in Utah, we have enough dissolved sulfur in the water and in the soil from gypsum and other things that we generally have plenty of it. But there are areas where we're seeing more and more sulfur deficiency on sandy soils where we don't have a lot of these stored up gypsum compounds and other things that provide sulfur over time in those systems. The micronutrients, the ones that we primarily look at least in fruit, are zinc, iron, calcium, copper, manganese, and boron. And we'll talk a little bit about each of these as we get into their management later on. But we're going to really look at the nutrient cycles and some of the main cycles that the primary nutrients go through. And you get a little bit of an idea of the need to understand the cycle in reference to how we manage that particular nutrient in the system. So let's start with nitrogen. We said it's one of the most important, if not the most important, that we manage on a regular basis. And the reason we focus so much on it is it's so dynamic in its cycling in the biosphere, in the natural environment. Now, this is it can be a little overwhelming slide here, but there's some key elements to this I want you to know about nitrogen. Our atmosphere is full of nitrogen. 78 to 80%, depending on where you're at in various places, is nitrogen. But we can't obtain that nitrogen. Plants and animals cannot put enough energy into nitrogen found in its gaseous form to separate the nitrogen apart and put it into elements that we can actually assimilate. We just don't have the energy complexes to do that. So the only way we can get all this wonderful nitrogen that's all around us into the soil and into the plant is a couple of different avenues, okay? Biological fixation, you see that on the right-hand side of the graph coming down from N2 in the atmosphere, is the primary way that nitrogen is introduced into the soil over time. Microbes in the soil, that's why it's important to feed those microbes, and they get the carbon and things from organic matter that helps feed them and facilitate their life. Microbes facilitate that breakdown of atmospheric nitrogen into forms that can be used by plants and animals. So bacteria like Nitrobacter and Nitrosomonas and others are responsible for bringing that down. Rhizobium bacteria, for instance, with in the root zones of legumes, help to fix and then to cycle those nitrogen compounds within the soil. And so those microbes are really the most important feature. We get a little bit of nitrogen that comes into the system from the atmosphere by way of lightning. And how many of you, when a thunderstorm's coming across from the West Desert, can we smell the advance of the lightning storm? Well, that's because the lightning has enough energy when it strikes to separate nitrogen, the N2 gas, apart, and then the nitrogen can then dissolve into the water in the atmosphere, and we get compounds like nitrous oxides and things like that that we can actually smell and detect very small quantities of with our noses. And so we can smell the advance of an electrical storm because of those nitrogen compounds that end up being in the atmosphere. Those can then be washed in to the soil with rainfall and things like that. But we only get about 2% of the nitrogen that is in our living systems from thunder, the activity of, lightning in the atmosphere. There's other processes we can go through that are chemical processes that we can then fix large quantities, high concentrations of nitrogen into mineral materials that we can use as fertilizers that can be introduced into the soil. But if you look at the soil cycle down below the big broad line there in the graph, everything that's below that line is happening in the soil. The microbes and the insects and the animals and the plants and things like that within the soil system are all competing for that nitrogen, for all of these important proteins and enzymes and DNA and other things within the cell. And so there's a lot of competition that goes on. There's a lot of changing of its structure into different forms so that it can be assimilated. The two primary forms that are used by plants and animals are ammonium, NH4+, and nitrate, NO3-. The plus and minus are indications of charge on that ion. Positively charged ammonium can stick to the surface of clay particles and organic material and be held and retained in soils. Because it's positively charged, it sticks to the surface of negatively charged things like clay surfaces and organic matter, like a refrigerator magnet. And it can be held there and stored for longer periods of time for plant and animal use in the system. Nitrate is negatively charged. What do you know about like charges? If I put a negative charge against a negative charge, what's going to happen? They're going to repel, right? They're going to repel each other. So nitrogen or nitrate, because it's negatively charged, tends to stay in solution, stays in the water inside the soil, and it moves rather readily from place to place. And so nitrogen is a very mobile nutrient in soils because of this. Because part of it, most of it, in most cases, once it's been converted, ends up in nitrate form, and it can move around quite readily in the soil because it doesn't stick to any surfaces. It stays in solution. And so that's the form that we're worried about losing when we over-irrigate or things like that, where we can leach it and drain it out through the bottom of the soil profile, where it's unreachable then by plant roots. Ammonium, on the other hand, would be the better form to keep it in if we can, to keep it stored in the soil, but it's so readily converted by all the microbes that are in there, changing its form, that it very rapidly can be converted to nitrate and lost. Both nitrate and ammonium are also subject to being converted back into gas forms and lost out through the atmosphere. So N2 and ammonia and nitrous oxides and things like that can be created, and it drives it back off. So that's why when we apply a nitrogen fertilizer or other sources of nitrogen, and it's converted really quickly into ammonium and nitrate, it's really only effective in the soil system for about 8 weeks. It goes through all these transformations so quickly, and it's in such demand by everything that's living in the system, that any application really doesn't have a long-term effect on the overall sustaining level of nitrogen in the system. That's why we encourage folks to either meter it in or split applicate or apply or things like that with nitrogen to try to prolong its availability within the system. If we put it all in a slug in the fall, we're not likely to have a whole lot of it left over later into the growing season because of this cycling that goes on. So that's one of the reasons why we do that kind of thing or promote that kind of thing when it comes to the management of nitrogen. We'll get into that a little bit more in detail later because of the way it cycles in the system. Any questions on any of that before we go through it? So nitrogen has the very most dynamic cycling system within both the atmosphere and the soil than any of the other nutrients. And that's why we focus in on key features of the cycle when we're managing nitrogen. We're watching to prevent leaching and the overconversion of things into nitrate forms. We're glad for the fact that it's mobile because we can get it from the point where we apply it to the root if necessary, or with the water or those kinds of things, which is nice, but we don't want to overdo it and then lose it out of the system. Let's take a look in comparison with nitrogen, the phosphorus cycle. Phosphorus is found in a number of compounds, mineral compounds within the soil, but the orthophosphate forms, the H, PO3, and PO4 that are up there, are the only forms that really can be taken up by the plant. So it has to be converted into those forms eventually, and that again is a microbially mediated process. So we can take it from a mineral form and process it into these. We have chemical and microbial actions that take place, and it converts it. Most of the mineral form that we find in our soils are calcium phosphates. But calcium phosphates are very, very, very insoluble in soils. Only a small fraction will dissolve naturally on its own. So how do we get phosphorus into the system? Primarily in fertilizer form, where we take a rock phosphate, like calcium phosphate, and we treat it with an acid to partially solubilize it so that when we put it in the soil, it can readily enter into these interactions that are going to change it into the orthophosphate forms. So if we look at the cycle, it's very much more simple than the nitrogen cycle. We have fertilizer sources where we actually apply mineral phosphorus, and we get this dissolution reaction that takes place to dissolve that phosphorus in, and it can be converted into the orthophosphate form. Or we have organic matter that comes in that contains phosphorus, and as it breaks down, it releases orthophosphate back into the soil solution. There are some other interactions that can take place, but the ones that you see down here with the iron and aluminum oxides at the bottom of this cycle really are not functional in alkaline soils. In high pH soils, above about 5.5 to 6, we get less and less and less interaction with iron oxides in soils. And so really just that upper part of the cycle is what's going on. It's either coming in as a source, converted to orthophosphate, and either staying in solution or going immediately into a plant, animal, or back into a mineral compound that is fairly insoluble. How fast do those reactions take place? Well, to give you an idea, if I take rock phosphate and I treat it with an acid like they do to produce things like triple superphosphate and so forth, of the fertilizers, once I put that soluble fertilizer source into the soil here in our high pH soils, within minutes, it starts to precipitate into rock phosphate again. It starts to go back into the insoluble mineral forms. And so this is one of the reasons why we manage phosphorus the way we do. It takes a lot of fertilizer to get the phosphorus we need into the plant typically because of this loss of phosphorus, soluble phosphorus into insoluble rock forms. It's also why we try to put it in forms that are hidden away from these chemical reactions that make it return back to rock phosphate. So organic forms and other things that we can introduce into the system often help us prolong the solubility or availability of phosphorus in the soil over time. So we're really battling, the biggest thing we're battling in managing phosphorus is the removal of plant available phosphorus into these mineral forms which lock it up in our soils. We have lots and lots of phosphorus in our soils, but most of it's locked up into fairly insoluble compounds. Any questions on that one before we go on? We'll talk a little bit more about this as we go along, and pH's influence on some of these as well. Potassium, another one of the big ones that we talk about being important. Let's take a look at potassium real quick, where it comes from. Almost all of potassium, in fact, 99% of the potassium that we get in our soil systems comes from the weathering of potassium containing minerals, primarily the clay minerals. And so you can see here a real simple representation on the left-hand side of this figure where you've got these clay sheets with potassium in between or within the clay structure as they're peeled apart and opened due to weathering and the breaking and things like that. Yeah.
So the small doses of water staying formed over time is much better for nitrogen and phosphorus.
In terms of keeping them soluble and available, that can be an effective. Oh yeah, repeat the question. Thank you, Marion. We had a question online that said, so metering in or small doses of nitrogen and phosphorus in soluble forms would be better overall in terms of uptake and use and things like that. It can be. It's been shown in some special cases to be a benefit over bulk application of those materials. The difficulty we get into with that is that you're applying it in a given spot. It may or may not be close to the zone of uptake. And so we don't always see a large benefit when it comes to metering it in. We always see a benefit to its being in soluble form, but we may not see it in terms of the productivity and performance of the plant just because it may not be where it needs to be taken up at any given time. And so if we can do a good job of placing that fertilizer where it's needed and so forth, particularly with phosphorus because it's not mobile like nitrogen is because of these chemical reactions we talked about. If it's near a plant root where it can be taken up and it's supplied in a way that keeps it soluble, then we do see a benefit from both placement and solubility with respect to phosphorus. Hope that answered the question a little bit. So potassium then is released as those clay minerals weather, and it releases that potassium into solution. Remember, potassium stays in solution. It doesn't enter into compounds in the plant. So it stays in that K+ form, which is one that can stick to the surface, outside surface of clays and organic matter and be retained in the system. So typically, we don't worry about potassium fertility in our western soils because we have lots of clay that weathers rather readily, that's potassium containing, and we typically get enough potassium from these soil minerals. However, there are situations where we have low clay contents, we don't have as much weathering that takes place, or we have a lot of intense uptake by a particular crop. We grow a lot of hay in the state of Utah and so forth, and we see a lot of deficiency developing in sandy soils that are heavily hayed because we're extracting it really fast and it's not replenishing very quickly. So potassium can, in certain situations where you have sandier soils, intensely cropped, and a lot of uptake, where we can start to see some deficiencies because it just doesn't get back into the system fast enough. So if we look at the cycle compared to the other two, then really the main sources are either the clay weathering, opening up that clay and releasing the potassium into the system, or it's coming in from an external source, a fertilizer source that we've introduced into the system. It shows leaching there with respect to potassium, but not nearly as much as we would worry about with nitrogen, because it is positively charged and it stays in the soil system, retained against movement by clay and organic matter in the system. So potassium is much simpler yet than even phosphorus or nitrogen. So you got a little bit of background now on the cycles and why we manage these nutrients the way we do. We focus a lot on nitrogen and phosphorus fertility in our cropping systems, horticulture production systems, because nitrogen is really dynamic. It's changing all the time. It's being used by every living thing in the system. And so we have to replenish it on an annual basis, typically based on the need of the plant. Phosphorus, on the other hand, we're constantly battling the disappearance of soluble phosphorus into insoluble compounds, which affects its availability over time. Potassium, we typically don't worry about it too much because we get a lot of it from our clay minerals, except in certain situations where we got to be careful. And if we see potassium deficiencies showing up, we then investigate it further to see if it really needs management in our systems. So let's talk about management here in terms of getting the information that we need to actually apply it in the amounts and location and times when it's actually needed by the plant. Good results in terms of fertility management always begin with good information. They say a blind squirrel finds a nut every once in a while, right? So I can put a dartboard in a dark room and somebody can say, well, throw the darts at the dartboard, and you know, I could probably hit the dartboard in the dark occasionally. But if I can see the dartboard, I may not still be very good at hitting the target, but I certainly know where I'm throwing them. And I get a much better result over time. So if we start with a good target, we have that firmly in view, we generally have much better results than just prescription applying what you've always applied, what grandpa applied, or what your neighbor's applying, or what the fertilizer salesman tells you you should apply, and those kinds of things. It's always good to start with an accurate target in mind. And so we talk about sampling both soil and plant tissues to help us determine what that target is and track our performance over time. So we start with current soil conditions as a basis, and we always want to make sure that we're sampling those soils as the plant's going to see it, and not as we before we do a bunch of different things with manipulating the soil and so forth. This is one of the questions that was one of our pre-course questions, was the best time to soil sample is when, and it gave you several options. The best time is right before orchard establishment. So after you've taken care of any kind of stump removal from old orchards, any kind of movement of soil, any kind of rebedding or reshaping of the field before you go back in and plant. Right before that is when you want to really test the soil, because then you're done with all the mixing and manipulation that's going to take place that will affect both the positioning and the forms that some of these minerals might be found in. So soil test right before your orchard establishment, and then every 2 to 3 years, soil sampling is then good as a anchor, a check to see that all of the management that you're putting into it with other things is actually tracking, keeping soil levels up and so forth over time. But the best way of determining whether I need or don't need a given nutrient is based on tissue analysis in the crop. Tissue analysis really addresses the true sufficiency of any nutrient in the system because it integrates everything that that plant is experiencing. It integrates the soil conditions, it integrates the water regime, it integrates the temperature fluctuations that are going on, it integrates any kind of disease, pressure, and other things that are maybe affecting the uptake by the roots or translocation in the shoot. It takes into account storage within the trunk over time and those kinds of things in the plant that we won't necessarily see reflected in the soil tests at any given moment. And so really tracking what's going on in the plant is the best way of determining whether a nutrient is sufficient or not, or in need at that point. And so both soil and tissue tests are needed to really get an accurate determination of nutrient need. And there's a couple other things that are affecting that, and the reason why we do both. Tissue reflects, like we said, all the conditions. It integrates all of that stuff that's going on within the environment and things. The soil, even though we see a deficiency developing in the plant, we may not see it in the soil. So I may take a soil sample and I say, well, I got ample quantities of plant available phosphorus or plant available nitrogen, et cetera, or iron or zinc or whatever it might be. But if it's not getting into the plant and I'm not seeing it in the plant, then it doesn't matter how much is in the soil. There's something else going on that I need to do to manage the availability of that particular nutrient or the uptake or translocation within the plant that I need to be aware of. And so soil may not always tell me what's going on and what the need is. Although that may be the case, recommendations for fertilizer application are still established on soil conditions. That was the original kind of basis for which we made recommendations for application amounts and so forth. And so a lot of the recommendations you receive when you get these tests would be based on soil quantities and soil conditions. So I need both. So how do I get the best possible sample to reflect conditions from either the soil or the plant? And so we're talking a little bit here about sampling tips and the way that I can get the best possible sample as I go along. What I'm trying to do with a soil sample and with a plant sample is to get the best physical average of conditions that that orchard is experiencing. I'm not going to manage every single tree on its own. I'm going to manage them more in blocks or in groups of trees. And so I really want to get an idea of the physical average of conditions that are taking place within that block so that I can manage it appropriately. I'm not going to change the fertilizer rate for every tree as I go down the aisle or the row, for instance. And so you want to know the physical average in that block. And to do that, we recommend taking multiple cores throughout in uniform areas, avoiding areas that may be anomalous to the block itself. And the top foot or so is the best in terms of the dynamics of what's going on in the system. Top 2 feet in some cases with nitrogen, for instance, on a deeper rooted crop like a tree may in fact be helpful. But we go through and we take them in random locations. If I do it on a systematic grid basis, I may or may not hit areas that are high or low, or I may hit all low or all high areas depending on my patterns. So a random pattern gives me a better chance of getting a good physical average. If I have a dissimilar area, I sample it separately, but I combine those samples and I mix them thoroughly into a composite sample. And then I take a subset of that composite and send it in for analysis. What I've done is I've created a good physical average of conditions within that block that can then be that can give me the most beneficial and management-worthy information out of that particular block. If I'm disinclined to do a lot of that and I just hop out of the truck at the corner of the block and I run in a few feet and I take a sample, it may or may not be representative of what that whole block is experiencing. And that's when we start getting into trouble with a recommendation that doesn't give me any response, or areas that end up being deficient when I've had what should have been a good recommendation for that, but was really only based on one location. And so one of the rules of thumb is that I don't want to represent more than 20 to 30 acres with a composite sample. So I would break them down into blocks that would be at least that small or smaller when I'm sampling, so that I don't over incorporate variability from place to place across the landscape. I'm sure you've noticed that in your orchards, that you can be in one corner of the orchard and it's got one soil type, and another corner of the orchard and it's got another soil type. Slope changes enough that the soils will be very different from place to place. And so don't try to represent more than 20 to 30 acres with a single composite, or you'll run into too much variability from place to place. What about tissue sampling? Again, we want to do the same kind of thing. We want to sample uniform conditions within the orchard, so we're collecting similar samples in appearance. We're also making sure that no other factors are affecting appearance. If there's obvious disease issues going on, those are going to confound the results I get for fertility, and so I want to try to avoid a lot of diseased tissue, for instance, and things like that that's going to influence that. I want to collect at least 10 leaves that are most recently mature on the new growth of the tree on at least 10 different plants. That gives me 100 leaves spread out throughout that block at shoulder height on the tree. That basically gives me a good estimate of overall translocation within the plant, as well as on individual shoots, so that we're getting that, again, average condition that tree is experiencing. Newest growth is very much different than the more mature growth, because it's rapidly expanding. Nutrients are both diluting and concentrating at different rates within those tissues, so we want to get back along that new growth to where we have the most recently mature leaf. So all of that dynamic is taken out of it. It's really kind of set as to what is going to be there in that leaf over time. And we want to take these after they've obviously fully expanded, and we don't get a lot of that change in content that's taking place. Yes, question in the group.
Dust content.
Yeah, that's the next point in our bullet list there. Dust content can greatly affect what we end up measuring. We get Tooele mud that blows in, right? And other things from the West Desert, and it gets deposited on our plants. That carries with it these nutrient elements as well, and we can confound the results if we have too much of that on there. Or if I recently went in and sprayed, it doesn't matter if it's a pesticide or a fertilizer spray or other things, they're going to contain these elements as well. And so we want to make sure that we lightly rinse the surface of the leaves to try to get as much of that off as we can. Don't scrub them. We don't want to disrupt the cells of the plant and release other nutrients out of the leaf. We want to make sure we get a lot of that dust and the obvious stuff off of those leaves before we send them in for analysis. We had a really good example of that in recent research that we were doing down here with one of my students in Santaquin area. She went in, actually it was in Payson. She went in and sampled a particular block. We had information that we were far enough away from a foliar application of zinc that we could go back in with a fair amount of confidence and do the sampling. Turned out that they had changed the order of the way that they had sprayed. We were in within a week of them having sprayed zinc on the orchard. And so she went in and we sampled, we sent them in, and we got these huge contents of zinc content, and it was because of the stuff on the surface, not in the leaf. So really, we had to go back and sample that orchard because we'd messed up. We didn't think we needed to do too much rinsing on those when in fact we did. So it's best to do that every time to make sure you get as much of that off as you can. Air dry those then don't put them out in the sun to bake, because that'll change the forms of the nutrients within the leaf and it could lose nitrogen. And for instance, you could drive that off back into the atmosphere by a lot of heat and sunlight energy. So we want to put them in the shade, let them kind of just surface dry, and put them in a paper envelope for shipping to the laboratory rather than a plastic baggie. You put them in a plastic baggie, there's generally enough moisture that's still escaping the plant leaf and things like that, that if it gets slowed down in transport, it's going to start to mold, and those cells are going to start to break down, and we're going to lose nutrients. They're going to change form and stuff like that. So put them in a paper envelope for shipping to the laboratory. That's the best way, and then they can process them further there when they get them. That makes sense. So again, it's this idea of getting enough sample at common locations of similar appearance so that we get a good physical average of conditions, and we're avoiding anomalous kinds of things that are affecting appearance, or that may be on the surface, like with dusts or sprays or other things that we want to make sure we get off before we analyze them. So how much do we actually need in these systems when we go along? And so we're going to look at some of the needs that we can kind of base our interpretation of results that we get back from the samples that we send in, and a little bit of the nuances with the different nutrients as we go along. So the amount that's needed depends a lot on, like we talked about, the soil properties, because of the cycling in the soil of these different nutrients. The crop management history. What have I actually done in the past in terms of putting fertilizer on? Are there stores of residual fertilizer in the soil that are going to be available to me that I can credit back to the overall need of the plant at one point or another? And so looking at the actual management history within that block or that field are going to help me to refine and adjust the need as I go along. Did you apply manure? How many of you are actually putting organic materials out or manures out or things like that in your fields? A few of you, a few hands. Those are rich in nitrogen and phosphorus, typically. They may or may not cycle into plant available forms over the time you actually need it or want it, but you still have to account for that in the overall need. You don't want to apply more nitrogen than you need, or we're going to run into environmental consequences and things like that with nitrogen leaching into groundwater and other things over time. So we want to account for that, and if we have time, we'll talk a little bit more about organic matter management in soils. If I know I've got a particular block, it's a more mature block, it's not producing as well as a newer block may be in a system, it's later in its life span and those kinds of things, but I'm still fertilizing, doggone it, with that yield goal that I had back 10 years ago on that block. I may be overdoing the application. And so there's all kinds of things then in terms of yield goal and the expectation for productivity on a given block that will help you also adjust the need that's there. And again, the best way of determining that is looking at the tissue and seeing what the sufficiency levels are and so forth within the tissue as we go along. And that helps you to go back and adjust if necessary. So we get the soil test results, we get the tissue test results back, and then we look at all these other sources that we can credit into the requirements. How many of you regularly soil sample and tissue sample? I hope most of you. What you're going to end up seeing on things, typically if you ask for fertilizer recommendations, is that they're really not going to do a soil nitrogen analysis unless you ask for it specifically. You're like, well, wait a minute. You told me that nitrogen's probably the most important and often most limiting nutrient. How come they don't measure that on a soil sample when it goes in? Well, nitrogen's so dynamic, there's so many things going on with it, that we recommend the application of nitrogen based on the annual need of the plant, regardless of what's in the soil. Unless we have huge quantities of residual nitrogen that we want to take into account. Like if we've been applying a lot of organic matter over time, we may have a buildup of nitrogen in the system and things like that. And we don't want to over apply and cause excessive vegetative growth and other things in the trees. So we have to account for that as we go along. But typically we base nitrogen recommendations almost entirely on content in the plant or the actual need of nitrogen over the course of the season by the plant. Not so much on what's actually in the soil, unless we know we are in a condition that we need to adjust it for. So when we do get those recommendations, what we try to do is target for what we see the performance of the tree doing with respect to nitrogen. So we're looking at within the first 3 years of block or orchard establishment, we're wanting to see on our plants new growth of anywhere from 16 to 24 inches, depending on the type of fruit. And I'll show you a table here in a little bit, which you also have in your handout, that'll adjust that. This is kind of average for, I think, cherry and peach. Apple may be a little bit different and so forth. But 16 to 24 inches of new growth for those first 3 years would indicate that I have ample nitrogen being taken up and used by the plant. It's the promoter of that vegetative new growth each year. In later years, I want to back off on that so that I don't over promote vegetative growth and allow the plant to divert resources into fruit production and bud establishment and those kinds of things in the plant, not push the vegetative growth. So we're only looking then for 12 to 15 inches of annual new growth as an indicator of adequate nitrogen fertilization. So keep that in mind as we go. There's some other fruits that were thrown in here from another presentation that you guys probably don't really care too much about, like blueberries and raspberries, but you see some of that same kind of thing in those canes. We try to control in the later stages of a planting the over production of vegetative growth by excessive nitrogen application. So we can apply more or less nitrogen then on various cycles depending on how much or more of that growth we need. Typical requirements, if we look at peach and cherry, yeah. After you've taken them, as soon as you get them rinsed and reasonably surface dried and packaged and set off, you want to make sure you get them there within a week once they've dried. We don't want them to get too over dry because we're worried about molding and other things. But within a week, if you can get it in there to them, they'll get it within a couple of days. They'll dry it right there immediately to a dry enough condition that will put all of the transformation of these nutrients into stasis to stop the changes so that they can do a stable analysis. But you got to get it into them pretty quickly. What we will do when we sample, for instance, is before I process the samples in terms of rinsing them and so forth, I'll put them on ice so that it's preserve them. I stop a lot of the microbial activity that might be on the surfaces of the leaf. I stop the actual function of the leaf itself as much as possible. So I'll put them on ice for a few hours until I can get them in where I can rinse them off, get them dry, and package to send off. If you're going out and just sampling one block and you're quickly going in and rinsing and drying them off and getting them off within a couple of days, you're good to go. Okay. Back to the typical requirements. So even though we're looking at the actual new growth on trees as an indicator of nitrogen sufficiency, typically that falls within a certain range of application of nitrogen. You can see down here the typical requirements at the bottom of this slide are anywhere from 0.01 to 0.04 pounds of nitrogen per tree per year of age, up to a maximum of 0.3 pounds of nitrogen per tree. Sean Rowley was a master's student of mine. He's up now in Idaho managing an orchard with his cousin up there. But his research down in Santaquin and Payson and other places indicated that on tart cherries anyway, the best result we got was with 1 pound triple 16 per tree. which works out to about 0.16 pounds of nitrogen per tree, which is about halfway in that range, which is kind of an interesting result there. Kind of an average point within the range was actually really quite useful and functioned well for Utah conditions. This was over a couple of years in his research, and I think a lot of you have adopted that particular recommendation to good result, and we hope to still get more feedback as we continue to look at these recommendations for the primary fruit crops anyway of our area. Yeah. Well, when we're looking at it, the question was, how do you gauge annual growth on the tree? You're just looking at that newest growth from the terminal bud out there, last year's terminal bud to the end of the new growth. And you're looking at once you've got most of the tree has the leaves have expanded and so forth. You're looking at that late June, early July period there where you're actually measuring that growth. There's not a lot of adjustment you can do for the current year, looking at the performance of the plant, because it's basically kind of set what it's going to be doing on the conditions that it's experienced previously. So you're kind of looking at what is happening so that you can adjust for future applications for most of these. And so unfortunately you wait a fair distance into the season until the leaves are fully expanded and that new annual growth from last year's terminal bud to the current end of the branch has finished elongating on there. Good question. So here's those tables I was talking to you about. Sufficient annual vegetative growth on the different plants that we deal with anyway, apple and peach and cherry are in that table there. And you can see for the younger trees, it's anywhere from 10, 15 to 24 inches. For the mature trees, it's much lower than that, in the range of 8 to 15 or 10 to 15 on average for the whole grouping there that you see. So as the tree matures, we want to back off a little bit on that annual growth. The nutrient content of the tissue itself that indicates whether or not the plant is sufficient in that particular element is in that second table you see in this particular slide. For nitrogen, phosphorus, and potassium anyway, not the minor nutrients. But that shows you what the content ought to be, and those are at percent levels in each of those nutrients in the tissue. So you can use these as a gauge when you get your soil or your tissue test back. Where you fall within that range will be a good indicator of how well you're doing in terms of keeping up with the need over time in the plant. I'll show you a little bit here too about some recent result on validating these particular sufficiency limits, which a master's student of mine recently completed here in Utah. So let's go back to nitrogen a little bit. We talked about it being only effective for about 8 weeks and kind of splitting it up. There's credit to organic matter we talked about, so we really already covered those. Phosphorus and potassium, the amounts available don't change that rapidly in soils, and so we can get away with 2 or 3 years. That's that cycle we say go back and track how you're doing because phosphorus, potassium really don't change that much in soils over that time frame. We already talked about phosphorus being important in seedling development. One of the things we haven't talked about is that excess phosphorus, too much applied and in soluble forms, can compete, detrimentally compete, with the uptake of zinc and iron in our soil systems. So if I say, well, you know, a little's good, but more is better when it comes to soluble phosphorus in my soil because I deal with the loss of phosphorus so much in high pH soils, I can go too far and then induce uptake competition for some of the micronutrients, particularly zinc, in our soils. And the reason is that zinc phosphates and other things precipitate quite readily as well, and that prevents those from getting into the root and up into the shoot. We talked about potassium not generally being deficient, and that we can get away with a longer cycle of return. But recent Utah research by my student Emily Tsai indicates that most of the time P and K are generally on our orchard crops in the state well within the sufficiency ranges, at least in terms of tart cherry and peach. And this was sampling done in Payson and in the Santaquin area, even over onto West Mountain and some over the Genola area, looking as many different places as we could for looking at these sufficiency ranges and checking them. And we found that most of the time, phosphorus and potassium are generally within the sufficiency ranges on our tissue tests. But that's early in the season. At bloom and a little bit later into the season, we see it high in the leaf content and the tissue content. But that as we get further and further into the season and closer to harvest, it drops. And it drops, understandably drops, as things are moved around and used in different places and diluted in the growth of the plant over time. It drops to slightly below sufficiency in some cases late in the season. So there is some opportunity for both potassium and phosphorus. We figured phosphorus because of the dynamics in phosphorus. But I remember I told you that we don't often worry about potassium nutrition. We have determined with this research that we probably are leaving a little bit on the table with respect to potassium nutrition in tart cherry and peach production in the state. So we may need to boost our annual P and K applications just a little bit to make sure that when we get closer and closer and closer to harvest, when it's really critical in terms of getting potassium is really critical in terms of fruit sizing and calcium translocation. So you prevent soft fruit and bitter pit and cork and corky conditions in apples and things like that might happen if you're too low in potassium as the fruit is developing. Tissue test criteria, again, are the important things, and we've noted that the ranges that we've been using for decades in the state of Utah are still functional, even for the current growing conditions that we find ourselves in the state, and the varieties and rootstocks that we're now using compared to what they were using back when some of these sufficiency ranges were first developed 50 years ago. That's good to know that we've revalidated essentially those sufficiency ranges and find them to still be functioning for our current conditions and varieties. Just a word on potassium. We talked about how important it is with the translocation. The third bullet there really emphasizes, though, the point that potassium is the most important of the nutrients for overall plant performance, and we don't account for that as much as we should. It's not as much an annual concern because it's not nearly as dynamic in its cycling as nitrogen. That's why we have so much focus on nitrogen. But we see more significant loss of yield and quality in fruits with low potassium nutrition than we do with almost any other nutrient. So we'd hope that we pay a little bit more attention to our tissue contents and looking for opportunities to boost potassium nutrition where it's needed. And you can go back and review some of this stuff here. Potassium is an important catalyst, like we talk about, moving things around. It's a solute adjustment for water relations, facilitator of sugar and dissolved ion transfer, important in disease suppression, and it's really important in fruit quality. Firmness of the cherry, for instance, both in sweet and tarts, is a function of good potassium nutrition, calcium nutrition, which is facilitated by potassium, good potassium nutrition. And the plant needs really as much potassium in the plant as it does nitrogen, or more in some cases, for adequate productivity and things like that. So There's some nuances here to potassium management. It's good to have it in before spring growth because it's difficult to change tissue content in any of these nutrients except for some of the highly mobile ones like nitrogen later in the season. But potassium isn't always thought of as being a foliar applied nutrient, but it is possible to apply potassium in a foliar application. How many of you might be spraying potassium? A lot of the apple producers will oftentimes do some spray there to prevent shoulder cracking and things like that that can happen with inadequate potassium nutrition in apples. And so they'll oftentimes do some foliar sprays, but they can be, if you notice you're having difficulty with soft fruits and bitter pit and cork pithy things in some of your fruit being developing, then you may want to take a look at trying to get some in-season potassium management going on in those systems. The ratio to calcium is really the kind of the key there. And so when we get our tissue tests back, if we don't see the ratio between potassium and calcium somewhere in the 4 or 5 to 1 range, we probably can boost either calcium or potassium, but generally a potassium deficiency will result in a calcium deficiency because of the translocation facilitation that potassium provides in the plant. So we look at that as trying to be the ratio that we maintain as much as possible in the tissue itself. These ratios are not well understood. They vary and they're fairly inconsistent, but that's kind of the target that we see most often associated with deficiency. I put this table in your notes. This is these are the interpretation levels that are associated with the soil test. We've looked at the tissue test tables here. These are the interpretation levels associated with the soil test results that you might get. And so we want people to have this kind of information in hand rather than just seeing the interpretation come back kind of in a black box result from the laboratory. So these are the ranges that we actually use when generating the interpretations when you send a soil sample into the laboratory and analysis. Now, labs may vary one to another on these ranges. These are the ones that the USU Analytical Laboratory uses. They'll vary a little bit if you send them to labs in Idaho or other places in terms of the adequacy levels that are stated here, but they're not far off from these. These have been chosen in the state of Utah to be what we call based on the sufficiency of that particular nutrient in soils rather than being well out onto the plain where crops don't any longer respond to further application of the nutrients. So we back off on that so that we're really only providing a sufficiency range that's associated with what we call the economically optimum amount in the soil. And so when you get different recommendations coming back from different laboratories, it's a difference in whether or not a laboratory has a mindset of building nutrient content in soil over time or just being at the breakpoint, the sufficiency breakpoint in the soil over time. So you can adjust your performance or your application based on that knowledge from any given laboratory if you know what criteria they're using for choosing their recommendation interpretation levels. Does that make sense? Any questions on that? A commercial laboratory, for instance, will tend to be higher in their recommendation. Why? They want you to come back as a repeat customer, right? That's a commercial business, a good business model to have if you're running a commercial laboratory. I don't want to give somebody a recommendation that may result in a slightly less than excellent result, because I don't want them to say, well, I don't want to go back to that laboratory. I want that return business. In a public laboratory like the university, I'm going to tell you what is the most frequently likelihood break point as to whether or not you're going to see a response to that application or not. And so I'm not so worried about being out on the upper end or the beyond sufficiency application point. So realize that when you get these recommendations back, they're going to be crafted with the mindset in mind of the laboratory that you're dealing with, and that's why the differences will happen oftentimes in recommendations. This is actually for more fruits than we had in the last table, but this is again just a table there for your reference of some of the tissue nutrient content that would be sufficient for these different elements. And this table also includes the minor or micronutrients: iron, boron, zinc, manganese, and copper, as well as calcium and magnesium. So these give you a little bit broader idea. And this is pretty universally used across laboratories. You'll see some nuances to the lower and upper limits of these sufficiency ranges, but if you stay within the midpoint of these sufficiency ranges, you'll almost always target a common result from laboratory to laboratory. Let's take a little bit more detailed look at sulfur here real quick. We said the sulfur deficiencies are uncommon in the West due to a lot of sulfate content. Gypsum is calcium sulfate. We got a lot of gypsum in our soils. As it dissolves and interacts with our waters, we get typically a lot of that there. It's available as sulfate that can be used by the plant. Additions are really difficult to track with soil tests. Yes? Yeah. Will the time of year influence a soil test result? Absolutely, yeah. And so you're always trying to take a soil sample at the beginning of when the plant's going to be actively taking up the nutrients, okay? And so as close to the time that the plant actually needs that nutrient and taking it up from the soil is when you're going to want to be sampling to get the most accurate view of what's available. If I sample in the fall, I've got all of the cycling and transformation that's going to take place during the winter, which does happen, and early in the spring it may affect then what actually is there available in the spring. So as close to the time when the plant's going to start using the nutrients is the best time to sample. Late in the season, we can go back in and take a sample to see in terms of overall use what might have taken place in the soil. We can use that as a gauge as to how much we've actually seen disappear from the soil or mined out of the soil, but we wouldn't use that then as a target value for the coming year because of all these things that can take place late in the season. Good question. Back to sulfur, the soil tests are actually quite ineffective for determining sulfur need. It's a difficult test to do accurately, and there's a lot of error in it. It's the best one we have, and we've looked at trying to develop better soil sulfur tests, but we definitely know that when we get below about 8 parts per million in the soil, we start to get into these deficiency conditions reflected in the plant. So unless we get into the real low soil test values, we don't really use the soil as the judge. The best is again the tissue sulfur there, and there's actually a fact sheet that we put together on how many times when we sampled 35 different fields across the state in hay production would we have misinterpreted sulfur need based on a soil test, and unfortunately it was quite high. So it was in the 60% of the samples would have been misdiagnosed as needing sulfur when we didn't see the deficiency actually in the plant. So look at the plant and use it as a guide with respect to sulfur. There's the sources that are noted there. A lot of them are 2-for-1 sources. What do I mean by that? A lot of times we'll get nitrogen from ammonium sulfate as well as sulfur. So you're getting a 2-for deal with these sulfur compounds. Potassium sulfate, for instance, gives us both potassium and sulfate. zinc sulfate. Most of the micronutrients are sulfate compounds that are soluble. So iron sulfate, zinc sulfate, and other things that you might be using as soil applied and foliar applied compounds will carry some of these other nutrients. So you have to account for them as well in the system. So, credit the nitrogen I'm getting from ammonium sulfate in my overall nitrogen need. You had a question? Some can be. The elemental sulfur is a very slow release. That was the question. No, ammonium sulfate is not. It's very rapidly. Urea is a little bit more slower to release the nitrogen, but ammonium sulfate is right now soluble. It solubilizes immediately into ammonium ion and sulfate ion, and both are taken up by the plant. Yeah, that's a good question on that. So these are pretty soluble compounds, but you get sometimes extra nutrition out of them, and you want to account for that in the overall need for those things. The micros, the most common deficiencies we see in fruit crops are calcium, iron, and zinc. Sometimes, but rarely, boron, and boron can be a real issue when it comes to crop quality and stability. The storage life and things like that of fruit and things like that. It can be a problem if you got really, really low boron. The issue with boron is that, again, the soil test is pretty bad for boron, and we don't often see a really good response to applied boron in the soil. So most of these, for real effect in the plant and changing the conditions in the plant when you see these deficiencies, will be through foliar sprays or slower release materials like chelated iron and zinc that will help keep them more soluble in our high pH soils over time. But generally, like I said, these are sulfate salts of iron, zinc, and calcium chloride or borate solutions and things like that. And the best determination of deficiency on these, because of the difficulty with the soil tests on them, are the tissue test levels. Since we've talked about pH as being kind of an issue with respect to the availability of a lot of these nutrients, let's take a look at what we mean by that and what's really happening here. So pH is the measured activity or concentration of hydrogen ion in soil solutions. The higher the concentration of hydrogen ions, the lower the pH. It's inversely proportional, meaning it's more acidic. There's more hydrogen there, it's more acidic, lower pH. Or higher pH, sorry, or lower pH, sorry, it's in the smaller numbers. Low pH water, for instance, acid solutions can be used to reduce the pH of soil in some cases. We'll talk about in cases that it cannot be. But in growth media and other things, it can be effective in lowering pHs. We'll talk about that here a little bit. And freeing up some of the things that are fairly insoluble at higher pHs. So why do we worry about soil pH? This particular figure shows you the relative availability of nutrients as a function of pH along the scale. So 7 is neutral. That's right in the middle of this particular figure. To the right of 7 is alkaline. To the left of 7 is acid or acidic conditions. Where do most of your soils lie, do you think? Roughly, you've probably seen it on your soil tests and other things. In that 7.5 to 8.5 range, typically in Utah, is where we'll end up being. The reason being is that we've got huge quantities of lime or calcium carbonate in our systems that buffer the pH to that level. If you look at the relative availability of the nutrients at that level, so halfway between 7 and halfway between 8 and 9, 7, 8, 8, 9, just go down through that column, you'll see that many of the nutrients are waning in their availability in those pH conditions, particularly the micronutrients, the iron, the copper, the zinc, the manganese, and so forth. they're forming really, really insoluble compounds at those higher pHs. They're much more available in acidic conditions. It'd be nice if we could make our soils more acidic and release a lot of those micronutrients that we deal with, but we'll look at the problem of scale in accomplishing that here in a little bit. So we're always going to deal with the lack of availability or reduced availability of the micronutrients, in particular at high pH. Phosphorus, look at the phosphorus figure there. It narrows down at about 8.5 and then opens back up again as other compounds are released. But if we get into those high pHs, we have problems with alkalinity that just kills the plant. It just can't tolerate those pHs anyway, so it doesn't matter if we get more phosphorus into solution. But at levels of pH that the plant operates well in, phosphorus is least available at that 7.5 to 8.5 range in our soils because of this creation of calcium phosphates in the soil. Nitrogen also backs off a little bit, but sulfur doesn't so much, calcium doesn't so much, and magnesium. They're all fairly available at these higher pHs. A lot of times when we see imbalances with calcium and magnesium, it's that we've got root function issues, maybe a lack of potassium nutrition that helps in the uptake and translocation of those in small quantities that's needed within the plant. So Western soils have very large reservoirs of pH buffer. We talked about this lime material, the calcium carbonate that's in our soils, and that keeps the overall pH of the soil up around the 7.5 to 8.5 range. In order to reduce or reduce the pH or acidify the soil, we would have to dissolve all of those buffering compounds that are in the soil, destroy them, or at least dissolve them all so that they're gone and have been consumed and neutralized before we can then begin to drop pH. So let's take a look at the reactions that are happening there and a little bit of the problem of scale we end up against in Western U.S. soils, particularly in Utah. So we're going back into high school chemistry here for a bit. Don't panic. There's no test at the end of this. You see on the left of the reaction at the top, this is calcium carbonate. That's lime, CaCO3. It reacts with carbon dioxide dissolved in water to form calcium ion and bicarbonate ion. The calcium is great because it's soluble, it moves about and can be used by the plants immediately. That's terrific. But the bicarbonate then enters into another reaction. The bicarbonate reacts with hydrogen, free hydrogen in the soil, which is what determines pH. That's the acid. And it consumes that. It puts it into a new compound. And the reaction that then takes place produces carbon dioxide, which is a gas, which goes off into the atmosphere, and water. So it completely neutralizes the acid. So for every molecule of calcium carbonate that's dissolved, I create 2 molecules of bicarbonate that consume 2 atoms of hydrogen. So I get a 2-for-1 neutralization of acid for every molecule of calcium carbonate that's dissolved in the soil solution. Well, that's why the pH stays right at about 7.5 to 8, because any excess hydrogen or acid in the system is so readily consumed by the little bit of calcium carbonate that dissolves into the soil water. So if we look at a graph that shows the change in pH in a soil over time, it stays at this plateau up at about 8 or so, as long as there's calcium carbonate present in the soil solution or in the soil profile. And it stays right at that as it dissolves because it's consuming the acid. There's no drop in pH. Once we've dissolved all of that calcium carbonate, that upper plateau, then we can start to see a drop in pH in those systems. There's other plateaus we're not going to worry about. That's the primary one that we wanted to see. But that buffering, that staying constant, is due to solid calcium carbonate in the system. So can I acidify my soil is the question. Can I get it back to an acid pH where I can actually free up some of these micronutrients that I constantly deal with, and phosphorus that I constantly deal with difficulties getting it into the plant. Well, here's the problem with scale. Our typical Intermountain West soils contain excess quantities of calcium carbonate in the range of 10 to 40% by weight calcium carbonate. 1% lime by weight in an acre foot of soil, that's 1 foot of soil over area, an acre in size, weighs 40,000 pounds. That's 1% lime in that soil. That would require almost pound for pound pure sulfuric acid to dissolve and neutralize that carbonate before I could even start thinking about dropping pH. But I don't have just 1%. I've got 10 to 40% calcium carbonate in my soil. So I would have to add 10 to 40 times that amount of pure sulfuric acid to dissolve all of that carbonate and neutralize it before I could even think about starting to drop the bulk pH of the system. And so when people ask me all the time, well, can I acidify my soil? I say, impractically, no. You can't afford that much acid. You wouldn't want to be dealing with it anyway. So why then do I do things like burn sulfur in sulfur burners to reduce the pH of my water when I'm applying it to an orchard? There are local benefits that can happen with temporary freeing up of nutrients that might be able near the root surfaces to be taken up and solve some of these, but they're very transient reactions and you're always going to be battling them. So it's one of those things that you got to just keep up with. If I stop doing any of that for any period of time, it's going to immediately release lime back to the system and cause that to be buffered right back to the same pH. And I'm back to the same problem with all of these pH influences that we talked about here previously. You've got carbonates coming in with the water. You've got salt compounds that have accumulated that are releasing calcium and magnesium that are also part of the buffering process that are going on there. So the system just wants to stay at about 7.5 to 8.5, regardless of what I do with adding acid to the system. We do add acid to the system with how many of you are doing sulfur burning on any of your orchards, treating your water? I know that a few of them are in various places around in Payson and Santaquin, so I've seen them. You've got to produce enough acid to neutralize the buffer compounds in the water so that I can lower the pH. So let's take a look at that issue real quick. When you're sulfur burning, what are we doing? We're rapidly oxidizing elemental sulfur. We're taking elemental sulfur, reacting it with oxygen and water, burning and then dissolving it into water and creating sulfuric acid. That's the H2SO4 over on the right-hand side of that first reaction. That sulfuric acid then dissolves in the water and releases hydrogen, reducing the pH. If I have anything, however, in the water, like dissolved calcium carbonate, for instance, that's going to consume that acid, it'll buffer the water right back to the original pH of the water, somewhere around 7.5 to 8, in our case, around here. So I have to put in enough sulfuric acid to consume all of that. So here's the problem with scale on water treatment. 1 milligram per liter or part per million of calcium carbonate dissolved in water neutralizes an equal weight of sulfuric acid, as we saw in the previous slide a couple of slides ago. 1 acre foot of water is about 1.2 million liters. So it contains, it would take about 2.65 pounds of sulfuric acid per 1 part per million carbonate to neutralize that carbonate at 1 part per million. But our waters typically around here have anywhere from 3 to 20 parts per million dissolved calcium carbonate. So if that's the case, and I have a pH of about 7.5, I'm going to have to put in anywhere from 8 to 53 pounds of sulfuric acid per acre foot of water to reduce the pH down to 5. Now 5 would be a good range for the solubility of a lot of our nutrients. But as soon as I put that pH 5 water onto a soil with high calcium carbonate, what's going to happen to the acid I produced? It's going to be almost immediately consumed. So I'm constantly treating water to get the water down so that when it infiltrates down around some of the active roots, I can get some benefit from some of the solubility reactions before it's all consumed and returns right back to the high pH condition in and around the root. We have seen benefit in some of our systems with sulfur burning if it's regularly done and it's added at quantities high enough to reduce the pH to a reasonable level that we can get some benefit out of. But it's a very transient benefit. It's going to, as soon as I stop applying that water, immediately return within minutes to hours to days at the most, 2 or 3 days, back to that high pH condition within the root zone. Any questions on that? It's one of those things that if you start doing it, you got to keep doing it if you're going to get any benefit out of it. Otherwise, it doesn't have any long-term effect. We've seen areas where we've put the equivalent of 10,000 pounds of sulfuric acid on a high pH soil. It drops the pH 3 or 4/10 of a unit down from about 8 to about 7.5, and within 4 days, it's right back up to 8 as it releases all of that soluble calcium carbonate in the system. Yes?
Would there be any benefit to, say, most of your iron is taken up in the spring before the leaves come on the tree? Would there be any benefit then to timing your soil acidification or increasing it during the critical period?
Yeah. Question from the group is, would I find any benefit since the trees taking up, all these plants will be taking up the nutrients that they need early in the spring? Would it be a benefit to me to try to do some acidification and things with respect to iron and zinc and other things early in the season in the soil so that that uptake can take place and be facilitated? And the answer is yes, but under certain conditions. We see some benefit, particularly in trees, where we have sequestered some of these elements like iron and zinc in zones of enrichment with acidic materials, where we keep them fairly soluble as much as we can over a short period of time. So opening a plug, for instance, and filling it with a 50-50 mixture of iron sulfate and elemental sulfur to try to create a zone of enrichment that's fairly acidified that the plant root can get into and take that up at that period of time, yes. Other things to try to hide it away from these reactions with pH is to use a chelate material that's stable at high pHs. How many of you heard of chelates before? We'll talk about them a little bit more as we go along. But chelates are organic molecules that hold onto and sequester these micronutrients. So they hold on to iron or they hold on to zinc, and it doesn't release the zinc until that material breaks down to a certain extent. It's organic. It's going to be worked on by microbes and other things. It's going to break down and start releasing those ions that are stored within it back to the soil system. So it's a slow release mechanism. The chelates, however, are not all stable at high pHs. So if I buy one that's an iron chelate that's not stable, it'll break down so fast in the soil that it won't provide me any benefit. So for our soils, the chelate that you want to be looking at is at EDDHA. So we can write that down, EDDHA. Or if you're just looking for an easier thing to remember, any chelate that's got a 138 number associated with it. It'll say sequestrine 138 or Miller's Ferry Plus 138 or something like that. The 138 is the indicator of that particular formulation of chelate. Okay. That chelate is stable at high pH. It is stable at pHs from 7 all the way up, or 6.5 all the way up to 9 or 10. It's fairly stable material in high pH conditions. So it'll break down like it should over time and release iron and zinc. So if you've got a chance to put some of this on early in the spring when the plant's really going to need it, has a chance to get some of that breakdown happening and the take up when the plant's actively searching for those micronutrients, then that's a good thing to do, that you don't have to worry about the acidification side to release the nutrient. So if you're using a chelate that's soil applied, you want to use the EDDH form or the 138 form. If you're using a foliar spray, that particular chelate is very vibrantly blood red when it's mixed with water. It can be a staining issue for fruit and things like that if you're using it as a foliar spray. So we don't recommend that much for foliar application, particularly when the fruit is on. So foliar application will typically be done with the 330 numbered chelate, which is DTPA. So you may see some Sprint 330 or some of these other compounds that are used for sequestering iron in particular. It's a really bright yellow color when it's dissolved in water, and it doesn't have near the effect of the staining and things like that that can happen with the blood red EDDHA 138 form. So yeah, 330 is the number of that particular chelate that you want to be looking at to probably be using in a foliar spray application. We all deal with salt in our soils. We're in an environment that has more evaporation than it does precipitation. So soluble minerals have been accumulated in our soils over time, and that's what salts are. They're just soluble minerals of various elements in our soils. We've got calcium chloride and sodium chloride and sodium sulfate and calcium sulfate, which is gypsum, and other things that have accumulated over time, eons of time, as those soluble minerals have been left behind as water has been evaporated out of the system. So we deal with salt. Typically, our salt levels in soils aren't at critical levels that are going to start causing some reduction in productivity or plant performance. We worry about high salts in soil solutions because it forms an osmotic barrier, a gradient for the uptake of water. Water interacts with those soluble the soluble salt ions in solution to an extent that it can't be pulled away from those interactions by the root and drawn into the plant if it gets too high. So we look at our soil salinity levels so that we can detect whether or not the salt solution is so high and concentrated that the plant root's going to end up with difficulty extracting it from the soil solution. For fruit trees, unfortunately, fruit trees are some of our wimpiest when it comes to tolerating salt in the soil solution. So they start to really suffer at levels of salinity, and I've put some values here. Don't worry so much about what the units are there. Realize that when we get into that 3 to 4 range in soil, we start to decrease in productivity just simply from what we call a chemical drought. We have an induced reduction in the ability of the plant to pull water out of the soil at higher salinity values than 3 to 4. So it's not an immediate precipitous like cliff drop off. It's a gradual drop off, but most of our fruit trees will back off anywhere from 15 to 25% per unit beyond that threshold. So for instance, if I'm at 6 or 8 in the soil, that's maybe 3 or 4 times or 4 units more. I could be looking at a 50% reduction in overall water and nutrient uptake by that tree at those salinity levels. So we got to watch out for the sources of salt in our systems. Compost and manures will carry it in. They themselves are really high in salt typically, and so if we put it on without accounting for that salt, over time it can accumulate to levels that will cause the whole bulk soil solution to come up in salinity. Irrigation water, as it concentrates in the soil after I apply it, if I have irrigation water at 1.5 decisiemens per meter, the unit that we use for conductivity measurement, if it's at 1.5, it'll concentrate almost immediately in the soil solution to about 3 to 4.5, anywhere from 2 to 3 times, or 3 to 4 times, sorry, what it might be in the water itself. And that just comes because we have this concentration effect that takes place as water used and it concentrates in the soil solution. So I got to watch for irrigation water. And if I'm using shallow water table sources for irrigation, I'm pumping it up. We want to know what the salt content is. Our valley locations, almost all of our water is affected to some degree or another, the shallow water anyway, with salinity accumulation. So you want to make sure that you account for that in your irrigation process. How do you get rid of it? The only way to get rid of it is to leach it out of the system. We can't apply anything that's going to neutralize salt like we can with acid neutralizing calcium carbonate or vice versa. It's not the kind of reaction that takes place with salts. We have to actually remove the ions from solution, so we have to leach them out of the profile. And so that takes higher quality water at higher quality at higher quantities of application sometimes to keep the soil profile from accumulating salts to deleterious levels. So watch for that in your soil test results. Most of the soil test results will come back in the Western United States with a salinity level, a salt content, to help you gauge whether or not you're at levels that are going to restrict water uptake and hence nutrient uptake. So salinity is closely tied to fertility, even though it's not a fertilizer situation, okay? It does come in with nutrient sources. It does come in with fertilizer. Fertilizers are soluble mineral salts of the nutrient elements. So if I put too much fertilizer on, I can also increase the salinity content of the soil if I leave residual behind on those elements. Yeah.
Can you use alfalfa? You cut it 3 or 4 times a year to take out salts?
If you're completely removing it, the question is, can I use, say, alfalfa or even my inter-row vegetation if I'm, having it take it up, and can I remove enough salt with that to make a difference? I'm definitely removing salt, but not in the quantities that's going to make really any difference over time. You're definitely reducing the overall quantity of these different elements. The ones that are left behind are fairly reactive. The things like the chloride and the sulfate and things like that that'll stay in the soils and won't be taken up large quantities in the plants are going to continue to affect things. And we just have huge stores of soluble salt in the soil already. So what we would call phytoremediation, or plants actually remediating a saline condition, it's very difficult to do it. Yeah. Leaching is still your best bet with these. Now, we have seen phytoremediation useful in things where you're talking about an element that's in very, very small quantities to start with that can be a problem, like too high a selenium or too high a boron. There are situations where they've used plants to effectively reduce the concentration. But those are elements that are in very small quantities to start with in the soil, but can cause issues with plants and animals. All right, let's take a look at some pictures. Yes. Oh, yeah, I can see the clock right there. Thank you. She just gave me the shut up time right there. That's good, because we're right on time. Let's take a look at some pictures. How are we going to detect whether we got issues? Let's look at some key features of some of these deficiencies that are going to take place. If I see chlorosis, you all know what chlorosis means. That's the yellowing of a plant tissue. If I see it over the entire leaf, it's happening pretty universally over the entire leaf surface, including the veins, but it's on older leaves, the oldest growth on the plant, then that's a typically indicator of nitrogen deficiency. If it's on the younger leaves, the growing points are universally chlorotic or yellow, then it's typically sulfur deficiency. If the yellowing is not happening over the entire surface of the leaf, but in certain areas or regions, like in between the veins, then it's some of the micronutrients that we're going to be dealing with that are deficient. If it's over the entire leaf and I see prominent dark green vein netting happening, that's iron deficiency. You'll all identify it almost immediately when you see it. If it's happening, I would also add, if you make yourself a note on there, you're going to see that developing on the youngest tissues as well first. Because iron just doesn't move that much within the plant. So It's going to be in the older leaves, but it can't translocate very easily from the older leaves to the younger leaves as they're growing and emerging and starting to expand. If it is on the older leaves and I see it starting at the tip and moving inward, these zones of yellowing, then that's typically magnesium deficiency. That's at the tip moving up the leaf. If I see marginal chlorosis, that's along the entire margins of the leaves, and as it progresses, it marches inward towards the main vein of the leaf, and that's manganese deficiency. And if I see any of the youngest growth, the newest growth coming out is really dark green or even purple or red tint to it, then that would be a pretty good indicator of phosphorus deficiency. Now, again, every one of these deficiency symptoms can be expressed if something else is perturbing the uptake and translocation of the nutrient. So I may have a root rot issue, or I may have a disease issue, or I may have a winter kill issue, or something else on a given shoot or tree that can also produce these deficiencies. It shows up as a deficiency in a nutrient, but it's mediated by some other event, not just a lack of that nutrient in the soil or in the plant. Does that make sense? So look, if you see a nutrient deficiency, make sure that there's nothing else going on that's affecting the uptake and translocation of the plant, the nutrient. When we talk about necrosis, that's the death. It's not just the yellowing, but it's actually the yellowing plus rapid death of the tissue. It tends to look dried or shot through or something else. So we get necrosis, or the dying or the burning of the tissue. If we see that along the margins of older leaves, but not on the younger leaves, that's typically potassium deficiency. If we see it happening within the leaf, along the central portions of the leaf or interveinal areas, it looks like almost a shot through, like somebody shot a shotgun through the leaf. You see these little necrotic holes that begin to develop. That's magnesium deficiency. Really advanced nitrogen deficiency would also be coupled with chlorosis at first, and then necrosis and the death of the plant. Now, if I get marginal leaf burning over the entire plant surface, not just on the younger leaves like with potassium, or the older leaves with potassium, but over all of the leaves, and I see it coupled with chlorosis, that's typically salt injury, because the leaf is just not getting enough water. The outer edges of it are beginning to dry, and things like that causes, that would be almost a similar type of thing you'd see in excessive drought conditions. If I'm looking at the morphology of the leaf, that can be an indicator of some of these deficiencies as well. What does the leaf look like as it's beginning to grow and expand? Young leaves will form kind of cups or depressions or gathers in the leaf if I've got calcium deficiency. Zinc deficiency results in these really small rosette groups of leaves that begin to form. You may get a rapid elongation of an internode and then a rosette that forms. That's pretty common with zinc deficiency. Young leaves that are stunted and misshapen and have very wavy margins can be an indicator, or is a pretty good indicator of copper deficiency. What about fruit? Fruit will also show deficiency symptoms, and I've listed some of these here. The cork spot or bitter pit in apples and pears, soft fruit in some of the other fruits, particularly in cherries and peaches, is a calcium deficiency issue. If you get gnarled, misshapen apples and pears and corky, dry flesh near the pit, that can be boron. We don't see that very often, but it's a really good indicator of boron deficiency. And they can show up in the fruit. These both calcium and boron deficiencies can show up in the fruit long before they show up in the actual leaf tissue. The reason being there is that you have just one more step of translocation with something that doesn't translocate very easily, going from the leaf into the fruit. And so it had a hard time getting in the root and up into the shoot. Then it has a hard time getting from the shoot into the fruit. And so sometimes some of these that are the micronutrients that are difficult to translocate from place to place will show up in deficiencies in the fruit even before they show up in the stem and leaf. So let's take a look at some pictures. They're not great, but they give us kind of a look-see here. So we're seeing some yellowing. It's beginning to develop all over the leaf. And in fact, as we go along, it's happening in the entire leaf surface in general, and it's happening on the older leaves. This would be nitrogen deficiency. Where we're seeing this necrosis or firing or burning along the edges of all the leaves on the older tissues, that would be potassium. You can see it a little bit here. That folded leaf that's there, prominent in the middle of the upper graph, you can see the kind of the necrotic tissue or the burn tissue along the very margin. On the grape leaves down below, you can see kind of the burned areas along the margins of the leaves, and those are on the older leaves there. That's potassium deficiency. Manganese, again, we said it's going to be an interveinal chlorosis, but it's going to start at the margins and march its way into the middle of the leaf. A lot of people will mistake manganese deficiency. If you can see the way that those leaves look with the prominent green areas kind of interveinal there, if you hadn't watched the development of that over time and you compared that to classic iron deficiency, you might mistake those two. So if you're following manganese deficiency, you're going to see it forming on the margins and gradually marching in towards the main vein of the leaf. Whereas with iron deficiency, it's going to show up across the leaf surface in all of the interveinal areas. So you're going to get this real prominent green netting of the veins that shows up in the leaf. And these, again, will be on the newer tissues first, the growing points. Sulfur looks a lot like nitrogen deficiency. You might look at that and you go, oh gosh, it's yellowed all over. That's nitrogen. I need more nitrogen. You put more nitrogen on, it doesn't correct the chlorosis, and it forces more vegetative growth. You don't want that. So if you're getting this kind of deficiency showing up on the growing points, on the newest leaves, rather than on the oldest leaves, then it's sulfur, not nitrogen. And again, a tissue test will verify that, but you can get a pretty good idea that you're going to need to sample and send that in for analysis if you see broad sweeping chlorosis across the entire leaf on the newest growth. Zinc deficiency, you see it more on the left example here in this particular picture than you do on the right. But you get this rosetting, you get elongating of the internode, and it's just a clump of the leaves, the rosetting. They don't fully expand, they look small and stunted, and they're closer to the stem than they would be. The petioles are shorter. Magnesium deficiency, again, it looks like that shot gun hit them, a bunch of little holes in the leaves. It's in the interveinal areas. They begin to yellow and then will die off pretty quickly. They'll burn and you get this necrosis that takes place. And then you got salt injury. And salt injury won't show up on the older leaves. It'll show up on all of the leaves. It's just a desiccation or drying out, and it begins on the margins of the leaf and works its way inward. Eventually, this is so bad that it's actually injured most of the leaf surface in this particular shot. Yeah. Yeah. Now you're getting into some real fruit physiology I'm not well acquainted with, but we have seen it where zinc deficiency will cause blindwood. It doesn't allow the bud to properly develop, and so you get these spots where you get where you should have fruiting buds and leaf buds and things like that just don't form properly. So if you see these big sections, and you can see that in this particular graph here, you've got areas in here which just don't leaf out properly and things like that, and they don't have the fruiting buds that happen, and that's a good indicator of zinc deficiency as well. Thanks, Ton, for bringing that up. The blindwood issue is is a good indicator of zinc deficiency. This I know is a strawberry. It's not a fruit tree, but it's going to give you some idea of the cupping that can take place. You can see the crinkling and cupping and almost folding in on itself of the leaves in some of these spots. The upper right-hand leaf is particularly affected. The lower middle leaf is particularly affected. You see these depressions and cupping areas beginning to form where you have calcium deficiency. And then I threw another salt injury one in here on strawberry. Again, you can see along the margins of the leaves, and it's over the entire plant surface that you see that happening, where the beginning of the salt injury is first expressed and then gradually moves in across the entire